things. First of all, as I mentioned, this method is based on determinants, and the right-hand side here of the equation, which is B1 up to Bn, plays an important role here. And also, I want you always to bear in mind that the interpretation of this column of the coefficients matrix. So this one here, for instance, it's the coefficients of x1 and here up to xn. So this is important. Now this method says the following. Then the solution of this system this is Kramer's method, is given by, okay, each xi, which is the solution. If I give xi for x1, x2, x3 up to the xn, then I solve the system. It's going to be the determinant of a matrix we will call A sub I divided by the determinant of A. So here in the beginning, let's require that the determinant of A is not equal to 0. So this is, I just added here on top, determinant of A is not equal to 0, because obviously we are going to divide always. So as you see here, the determinant of A is a so-called common factor by all. Now, what is AI? What is AI? AI is the matrix where the ith column is replaced by the right-hand side. So B1, B2 up to Bn. So in this way, we can solve the linear system straightforward just by constructing these determinants. Now, this method, I hope that you got the idea of how to use this method. If you didn't get it completely, don't worry, because we are going to solve an example in short. But the nice thing about this method are two things. First of all, it is easier to solve compared to the other two methods. So far, if you remember, the method we introduced so far is the Gauss elimination method or the Gaussian elimination method, whether you reduce to echelon form or reduced echelon form. And the second method was part of this morning's exercise was, I think, question number 2 is solving linear system using the matrix inverse. And the third method that we are introducing today is Kramer's rule. Now is usually the student's favorite. That means if you leave it for the students to choose which method, they will go for this one. So this is just because, as you might notice, when you work with the reduction of rows and columns and all these calculations, you can easily make errors, calculations errors, and you will be stuck somewhere. So that's why it's considered by many students as the easiest method, and it is always or most of the students choose it when you leave it for the students. Now, another thing is nice about this method is when you just solve a linear system using the previous methods, you need to solve the entire system. That means you need to find the value for X, Y, Z, and so on. But in this particular one here, you can solve the linear system. You can solve the linear system only for one particular variable. That means, for instance, if you are an engineer and you have an equation that involves different an equation that involves different variables, or system of equations that involve different variables, and then you are only interested in the value of one variable. That means in this method you can solve for this particular variable. No need to solve it for all other variables. This is the one of the advantages of using this method. Now let's turn to an example and see how to solve a particular linear system using this method. So let me just give you the example first. So this example is a three variable system, and it says here solve the linear system using Cramer's method. Okay, so it specifies a method here. Okay, so obviously if I keep asked by students, do I have to use this method? In this case, you need to use it because obviously it's stating that use this particular method. All right, so the linear system is given by 2x plus y plus z is equal to 3, x plus y minus z is equal to 0, and x plus 2y plus z is equal to 0. Okay, so first step here, we need to try to get this system in the so-called matrix form. Okay, so first step here, you write the system in matrix form, and usually in the exam I give points to this, and not only it's recommended. Usually, if you are solving mathematics and you have question with different, let's say, sub parts there, usually the solution is built on each other. That means if you have question where you have A, B, C, D, whatever, so usually you need one step. If you solve it correctly, it will simplify getting the answer of the next step and so on. So please always work systematically. So in this case, you just write it in the form. Now, before that, let me just go here to this equation, system of equations here. So let me check 2, 1, 1. So here 1, of course, by default, this is 2. This is 1. So by default, if there's no number here, it means it's 1. So this is negative 1. This is 1. This is 2. And this is 1. Okay, so obviously this green labeled are the coefficients matrix. So the system here as AX equals to B, it could be written this way. So this is A. This is 1, 1, negative 1, 1, 2, 1. Now the variables matrix, it is X, Y, and Z, which is capital X here. And simply here, this one is, let me just write it in red because as I told you, it is, so 3, 0, 0. Okay. Now, this is obviously A, this is capital X, and this is the right-hand side, or we labeled it with capital B. Now, to solve this system using Cramer's rule, first we evaluate the determinant of A. Now, always before you start solving any system of linear equation, evaluate this determinant because it will give you an idea whether this system has a trivial solution or not. So if it's 0, then the system can't be solved using this method. So you have to stop and leave it there. If not, then you need to evaluate it. Okay, so the determinant of A is equal to 2, 1, 1, 1, 1, negative 1, 1, 2, and 1. Okay. Now let me check how many students we have in line. Online, very, very few students. I don't know what's wrong, but I hope those 4 or 5 students who are online know how to evaluate this determinant. Remember the rule, so we said that you take this element, this is negative here, then you take this element, then you take this element, and then you cover the row and column where the first element occurred, and then you will be getting a reduced 2 by 2 determinant. And then we know the rule for a 2 by 2 determinant is that you multiply across this diagonal, subtract by the multiplication of this diagonal. So I want you just to give me an answer for this one, please. Just make sure that even the few who are joining are not still there. So, waiting for answers. No answer. So, first determinant. Five. Okay, let's see other answers. Now remember the fact that a 2 by 2 determinant is, let me just write it here somewhere on scratch paper. So a 2 by 2 determinant, you just have A, B, C, D. And we said this method is just you multiply A with D and then subtract from C times B, right? And this method, that this is one of the methods to evaluate the 3 by 3 determinant. We spent a class when we talked about cross multiplication or cross product of vectors. And I showed you 2 methods there. One of them is the Leibniz method, and the other was the diagonals, adding 2 columns. Now, This method is a typical method that is called reduction method. That means you will start with any order of square matrix, and then you will be covering rows and columns, reducing it until you get to a 2 by 2. When you get 2 by 2, you know how to solve it, okay? So this is one method here. So let's try to solve this one. So it's 2 times, if I cover this row, this column, I'm left with this 2 by 2 matrix. So 1, negative 1. Okay, I see that only Amna is reacting here anyway. So this one is 2, 1. So I just cancel this row, this column. Negative. So the second column here is negative. Then I take this 2, sorry, this one, and I multiply it with the result of the reduced determinant. So if I cover this row, this column, I'm left with 1, negative 1, 1, 1. 1, negative 1, 1. And the last one is, again, this one, I cancel this column, this row, 1, 1, 1, 2. So 1 times 1, 1, 1, 2. Now I know how to evaluate this 2 by 2 determinant. So this one simply is going to be 2 times 1 times 1 minus 1 minus 2. So here it will be negative 2. Here minus 1 times, here I have 1 minus 1 is 2. Yeah. And here I got 1 times 2 minus 1. I hope we didn't make any mistake there, right? So here again 1, negative 2, so it's 4. This is 4 minus 2 plus 1. Uh, Definitely we made a mistake there.
Wouldn't there be the first number has to be 6 because it's uh
So
2 bracket open 1 and then there's minus 2.
negative 2, 2 times 1 plus,
Yes.
this is 4. Here 1, negative 1 minus 1, 2. This one 1, 2 minus 1.
Oh, why are we skipping the first 1 into 1?
1 minus, this is 3, right? 1 plus,
Yes, 1 and then won't we write 1? Yeah, here.
this is 3, this is 2. So end up of having,
Isn't it 6 instead of 3?
okay, so I have here 3. We have here 6 minus 3. 6 minus 3. Okay, it's 3. Now the important thing here is how to construct the two other determinants. Let's see. Check this one here. Okay. Now let me write D again here just for for orientation. So we said that D is equal to 2, 1, 1, negative 1, negative 1, 1, 2, 1. Yeah, so this is D. Now D sub X. Now remember that B here is just the right hand side, so it's 3, 0, 0. And let me again here label it with red because it plays here an important role in this method. And this is here also, as I told you, bear in mind that these are the coefficients of X, these are of Y, these are of Z. Now what we are going to do to create D sub X, we are going to replace this first column with this side here, okay? The right-hand side. So here I have 1, 1, negative 1, negative 1, 2, and 1. And here the right-hand side, I have 3, 0, 0. And this determinant I call D sub X. So that means I'm replacing the first column here where X coefficients occur with this column. Then D sub Y here, D sub Y. And this I'm going to replace the second column. So again, I go to the first one here, 2, 1, 1. Here I have 1, negative 1, 1. And here in the middle here, now I have the coefficients of y. I take them out and exchange this with the right-hand side. Okay, so this is what's called E sub y. And the fourth determinant here we are going to construct, it's called D sub z. And this is equal to, okay, so here I have 2, 1. Always go to the original determinant here, 1, negative 1, 1, 2. And then here I replace the third column with the right-hand side, 3, 0, 0. Okay? Now let's evaluate these matrices. Okay, I'm going to replace this with these here. So here I will be having 3 times negative 1 plus 2. Then I have here minus 1 times 0 minus 0, because here I have 0, 0. And the last one here is 1. If I cancel this one here and that one, 0 times 2 is 0, 0 times negative 1 is 0. So here, so here I have 3 times negative 1 plus 1. So it's 3 times 1, which is 3. This is 3. So this one we evaluated as 3. Okay, so D sub y now, D sub y. So 2 times 2. So I cancel this and that. So I have here 0 minus 0. Okay, because if I cancel this, that, so I have this determinant 0, 0. Then the middle one, I have minus 3 times 1 minus minus 1 plus 1. Plus 1. So if I cancel these two, I have here 0. So 1 times 0 minus 0. And this is equal to 0. 3 minus 3 times 2 is minus 6 plus 0 and this is -6. Okay. So as you see here, this whole procedure here, it depends entirely on the ability to evaluate determinants. So that's why I urge you for I don't know which time to recall your memories and just make sure that you understand how to evaluate the determinants, not only for this section, but here it's very important. Okay, now let me just evaluate this again. So to cover this one you have negative, so 0 times -0. Then you have 1 minus, of course, here 1. Again, here you got 0 minus 0 plus 3. Then here you got 2 minus minus. So here you got 2 plus 1. So this is equal to 0 minus 0. 3 times 3 is 9. Okay, so now the thing here is after I evaluate the determinants, if you go to the rule, it says that each variable, for instance, to solve for x, you divide d sub x by d. To solve for y, you divide d sub y by d, and to solve d sub z, you divide d sub z. So this is what the rule says. So the solution is given by of the linear system x equals d sub x over d. Notice that here everything is divided by d. So here I have both were 3. So 1 is the value for x. And here, I hope you see why we require that determinant d of the coefficients is non-zero, because you are dividing by this all the time here. So d y is equal d sub y over d, and this is equal -6 over 3, and this is -2. And finally, the last variable z is equal to d sub z divided by d, and this is equal to 9 over 3, and this is equal to 3. All right, so that means that the solution here for all the linear system is x, y, z is equal to 1, -2, and 3. Okay. So I hope you got the advantage of this method. This method, by the way, it's as I told you, it's maybe a favorite method for many of the students. Understandable why, because it doesn't include complicated calculations. And also, if you want to solve for one variable, for instance, here, if you are an engineer, you have this relation given by this system of linear equation, and you are only interested about the value of, let's say, the variable y. So no need even to construct this determinant, that determinant, just go substitute the column where y variables occur, and then divide this determinant by the determinant of the coefficients, and you got your answer. So this is in contrast to the other method, because other methods you need to give the solution for the linear system for all variables, and then you choose the variable that you are looking for. So in this case, it is a bit easier. Okay, so any questions? regarding this method. 6 is correct. You are talking about this determinant. See, uh, 2 and 1. Did we make a mistake here? Let me just check it in the script.
No, sir, I was wrong. I was confused about
Alright,
something.
we have here, yeah. Please correct this. This is a negative, yeah. So this is a negative, and this one is a negative. Okay. Then this determinant is negative, negative. Then this middle term will be. Let me just check it. So here you have. Of course, this one negative 1, 2. Okay, so 2 negative 1 negative 1. This one. Okay, so negative 1 negative 1. So you have negative 1 plus 2. So here you have 2. In the middle here you have. Okay, so you cancel this one here. 2. So here you got 2 and this one negative 2. And the last one here you got this one here. 2 plus 1, which is 3. So this one will give you 3. This gives you now it's okay. Now it's okay. You have this cancels out. You left with 3. Okay, so please just correct this one to negative y. Then accordingly the determinant. So here we wrote it correctly. This one we wrote it correctly. So you can just easily evaluate it using any method and check whether it's 3. I hope now it's clear. I'm sorry, there was a minus there instead of the positive one. Okay, so is this here? It's not working. Yeah, I have a problem with the mouse. What happened here? Anyway, I hope you still can see me. My laptop is freezing. Can you say something? Can you hear me? I can't do anything with this.
Yes, we can hear you.
Oh, I'm sorry. Maybe I need to restart my laptop. I don't know what happened. It's just freezing. The mouse is not reacting. The touch screen. Hmm. I don't know what to do now. So can you just try one more try? Huh?
We can hear you.
How was it? Control F. Okay, I hope now I fixed the problem. You can see and hear me again. All right. Can you see me and hear? Yeah, at least see the projector here? There was an issue with laptop. I don't know what happened. Okay, now we will continue with determinants. Here maybe two remarks. I see that I don't know what's wrong this week, but many students they are not joining. I hope. What happened here? What's going on today? No. Okay. Fixed. Okay. Now the thing is, evaluating determinants is something that you need to exercise if you want to work with this particular method. However, sometimes evaluating determinants is easy, okay? Sometimes it's easy, and sometimes there's a shortcut in a couple of cases. Let me give you one of these. So for instance, if you are asked to evaluate the determinant, uh, of, let's say, 3, 0, 0, 2, 0, 0, let's say 2. Okay, I hope you can see it. I have here 1, 2, 3, 4, 5 or 6 students are online. Just I want to give you a couple of minutes to solve it. Anyway, you know, either this method where you duplicate these two columns here, and then you take the diagonals, falling diagonals. So I'm not saying it's 6, right? Are you sure? So I want to see some more answers, yeah, because I'm going to show you a very interesting shortcut here. So please. Any other results? Okay, so let's see. There's another value here. 0 multiplied bunny, I think, well, is 0, so it's just assume it's 6. Okay, if you try just to apply the method we used before, okay? 3, then cover these rows, these columns, then take this one and see what you get. Okay? Hiram, Islam, Falikan, and Nilutbal. Do you have answers? Hiram, you're saying it's 12 or minus 12? 12, okay. Okay, looks better, right? Looks better. Now the thing here, if we apply the method we know, so it's 3 times the rest here, which is this determinant, right? 2, 0, 0, 2. And everything else, this will give me 0, this will give me 0. So here I have plus 0, plus 0. So here this is going to be 3 times 4 minus 0, which is 12. Now, look at the values here along the main diagonal. So this value, and this value. Now, if you multiply these values along the diagonal, you will be getting 12. So here in this case, it's 3 times 2 times 2, which will give you the value of this determinant. Now, this applies also for, maybe I didn't tell you this information before, but you might know it, that if you have a determinant actually can be evaluated according to Leibniz if you use any row or any column. Okay, so that's why if you have a large determinant, let's say 4 by 4 or 5 by 5, and you have a row or a column where you have many zeros, then you can use this instead of using the first row here as we do it again. Now, this will work for such matrices where you have zeros upper and lower from the diagonal, but also it will work for okay, if you try to evaluate this determinant, try to evaluate it. Let's see what you get. You see, this is upper triangular. So here you have, it's not like the first one. You have here the main diagonal, then you have zeros here, zeros there. It is only on one side, which is the lower side, zeros. So I just want to see some answers there. What do you get? Okay, so you also got 12, right? Which is true, which is multiplying all also these diagonals. So that means wherever you have a matrix where the upper triangular form, or if you have only the diagonal, all other values are 0, then you just multiply the main diagonal values and you are there. This is the value of the determinant, okay? So don't get confused if you see, I don't know, somewhere in the exam or in some assignment, a 4 by 4 determinant, which is actually either lower or upper triangular form, then you just multiply the diagonals and you're there. Now here you see, also I can evaluate along this column. If I do that, I need, of course, here plus, minus, plus. Then I will be having 3 covering this. Then I got here 2, 2, 4, minus 0 times 3 will give me also 12. And the others will give me 0. So here, this is what I was telling you about, that you can choose whichever method you want to evaluate the determinant, using which method you like. But as you see here, it is it's all this method is, it's all about evaluating determinants. So Kramer's rule, again, to summarize it before we go to small break, is you have to construct for each variable an additional determinant by replacing the column where the variable occurs with the right-hand side column. In addition to the original coefficients determinant that you need to evaluate the variable. So that means here, if you have 3 variables, then you need 4 determinants. If you have 5 variables, you need 6 determinants, and so on, because you need one more, which is the coefficients in addition to the determinants that are generated for each variable. Once you do that, then you divide each corresponding determinant by the determinant of the coefficients, and you get the value of the variable, which is the solution. Okay, so this method is actually, as I mentioned, favorite by most of the students. Now, before we go to the break, I want just to show you something here. What we learned throughout this chapter, this is actually the last lecture in this chapter. So what we learned so far is the following. We learned how to solve, which was the title of this chapter actually, systems of linear equations. Now, you know that for a 2x2 system, it's pretty straightforward, and you have their methods like substitution and also elimination. But we just starting with three variables, we made it a little bit more structured, and this was using the so-called first method using the Gauss or Gauss-Jordan elimination methods. Okay, so you remember there, and there we use the so-called elementary row operations, and related to this, we obtain the so-called echelon form or the reduced echelon or echelon reduced form, as it's sometimes referred to. Okay, and this method is actually requires, if I have the system here of linear equation as ax equals to b, now here you just start by the augmented matrix A, then you add to it to the right here B, and then use the elementary row operations to get it into either the echelon or the reduced echelon form. Okay, this is how we worked on that. We had lots of exercises how to apply this method either to reduce to an echelon or reduce echelon form. Do you have any questions regarding this method? Any questions? Obviously, this method requires, of course, yeah, some, let's say, fine feeling for the steps, right? So whenever you are using this method, you have to maybe carry out each step as I advised you on maybe a separate paper, just to avoid any problems with calculations. So maybe you keep a scratch paper on the side for just carrying out these steps. And by the way, the elementary row operations, the three operations we had, adding or subtracting two rows from each other or to each other, multiplying by a non-zero or dividing by a non-zero, and the third operation is simply swapping the order of the rows. Now, the second method we learned, and today we had exercise number 2 in the worksheet this morning, which is using the A inverse method. Maybe here, let me assume here that the determinant of A is non-zero, okay? Here, this is an important condition because if the determinant is 0, you will be stuck if you use Gauss or Gauss-Jordan elimination methods, you will reach something that definitely will be either a tautology or a contradiction. And this is, of course, not desirable. So here, before you start, check whether the determinant of the coefficient matrix is non-zero. Okay, we saw some examples that if this is not zero, that means here you will be just having some contradiction, like a number is equal to another number and so on. And this is also, it has to do with the existence of the inverse of a matrix. So if the determinant is non-zero and the matrix is squared matrix, then it means the inverse exists. Okay? Using the inverse method, if it exists, and this is equivalent to determinant of A is not equal to zero. So you see here, determinant of A is not equal to zero. It's important if you are trying to find the inverse of a matrix or solve the linear system and so on. So it's in linear algebra, it's a very fundamental concept that's why I will strongly advise you to, before you start solving any linear system, you just check the determinant of the coefficients matrix. Okay, so if it exists, then what we do, we multiply from the left. Now, today we will, okay, so here, as you see, this equation here, this equation, just multiply from the left with the inverse. This will result in I, which is the identity, and this will give me X, and this will give me A inverse B. So that means here, that means the values of X, which is the solution, is just A inverse times B. So in other words, if I know the inverse matrix of the coefficients, I multiply it here, maybe you multiply from left. This is important because we saw that multiplication of matrices, it's not commutative. That means A multiplied with B is not equal to B multiplied by A. In fact, that sometimes A times B is defined and B times A is not only, it's not equal, it's not defined at all. This could happen. Okay, so evaluate the inverse, then multiply it by the right-hand side, and this is the solution of your linear system. And the last method we learned today is Kramer's rule, which is dependent of the determinants. So there, the challenge in Kramer's rule is to construct the n plus 1 determinants, where n is the number of variables, and then after this, it's just straightforward, like we did it earlier today. Okay, so these are the three methods for solving linear systems. Now, another thing that we learned in this chapter is working with determinants and matrices was also a topic. So here, matrices, yeah, working with matrices. Now, I just want to remind you about working with matrices about two things. The first fact is that matrices are not, matrix arithmetics. We have addition and subtraction. Okay? This is defined for same dimension matrices. Okay, that means I this is actually a major difference between matrices, for instance, and real numbers. Real numbers, you can add and subtract any two numbers to or from each other. However, for matrices, before you start applying the operation, you need to ask yourself, is this defined, yes or no? If it's not defined, it makes no sense to just start evaluating. Now here is important that both matrices are from the same dimension and the result will be also from the same dimension. For instance, if you are adding a 2 by 3 matrix to another 2 by 3 matrix, the result will be 2 by 3 matrix. Okay, so before you just start evaluating any of these operations, please ask yourself, does that make sense? Is it defined, this operation? Yes, no, and then you can just start evaluating. The second thing here is that we have, usually at school, you learned multiplication, right? And you learned also division, right? Now, multiplication, addition, subtraction of matrices is defined. Multiplication is defined. I will tell you in short the condition. However, division is not defined. So division of matrices is not defined. It doesn't make any sense to talk about division of matrices. And that's why we will learn in the next session how to solve still. If you have multiplication, you don't have division. How would you get rid of variables? I will tell you in short just to prepare for the next session. But before that, multiplication. When is multiplication is defined? A times B is defined if number of columns of A is equal number of rows of B. Number of columns of the one to the left is equal to number of rows of the one to the right. If this is the case, then it is defined. Okay? So it's not defined always. However, for two square matrices with the same dimension, it's always defined. It's always defined. And not only that, if I have two matrices, let's say I have a matrix that is M times N, and the other matrix must have, this is N columns, so it must have N times, let's say, K. So if I multiply these with each other, these inner numbers are equal. The resulting matrix is going to be M times K dimension. Okay? So this is how we construct the multiplication. Okay, now division is not defined. What to do? Now the next topic for today is solving what we call a matrix equations. Now if forget about matrices, if I give you numbers, okay, I tell you 3x minus 4 is equal to let's say I don't know, 11 minus 2x. Okay. Okay. If x and y, okay, x and r, and solve for x, what is the solution? What would you say here? How would you solve this? How would you solve this? What are the steps here to solve this simple? Isolate x. Okay. How will you isolate x? Okay, so you will be having here, let's say 5x equals 15, right? Now the next step, what do? You divide by 5, right? To get x equals to, let's say 3 here. Okay. Now if we work with matrix equation, we don't have division defined there, right? Division is not defined. How to do? Here, instead of dividing by 5, we can multiply by 1 over 5. Okay, so here 5x multiplied by 1 over 5 is equal 15 multiplied by 1 over 5. Why 1 over 5? Because 1 over 5, if you like, is the inverse of 5 under multiplication. And this is the trick we are going to use to solve the equations involving matrices, even though we don't have a defined division. Okay, now, of course, I will repeat it. Now, if you have 5, end up of having 5x equals 15. Now you want to solve for x, right? Now, obviously here in numbers, you will say I will divide by 5, okay? But imagine you don't have division is not defined, like in the matrices. What would you do? You will say it's 5 multiplied by 1 over 5, x equals 1 over 5. Now, instead of dividing by 5, you are multiplying with 1 over 5. Where 1 over 5, if you like, 5 inverse is equal to 1 over 5. And this is obviously because this will give you the identity, which is 1. You got it? Which means here, okay, which means here, when we work with matrices, we will use the fact that, if for instance, we used it actually for solving using the inverse. So here, if you have ax equals to b, we want to get rid of a. We can't divide here, right? It's not allowed. No problem. What we do here, we will just multiply by the inverse to get rid of, because this will give me the identity. And this is how we will work on solving linear equations, or sorry, matrix equations. Important here, since we don't have commutative behavior here, that means here multiplying here, in this case from left or right, you need to be careful, okay? It's not the same. So that's why after the break, we will talk about this in more details, and I will show you how to decide whether I'm going to multiply now by the inverse from the left or from the right. Okay, so after the break, we will meet and then talk about this method of solving the equations involving matrices and how to come over this problem that we don't have division of matrices defined at all. Okay, so see you on, let's say 11:30, okay? 11:30. Thank you. Questions? Do you have any questions right now? Okay, so let's take the break and then we meet, as I mentioned, 11:30. See you then.